There it goes. I guess. The problem is we're going to see it can't go the whole period so far. So I put some things into effect that hopefully the battery will last a little bit longer. So far it has a range of about 30 minutes, which is, but anyway, we're going to give it a try. This is good too. Okay, you wanted lights off? Lights off? Okay. All right, ladies and gentlemen. So as promised, we're going to talk about half-life. Again, nuclear, easiest algebra or easiest math you've ever done in any science class. Half-life is just the time it takes for half of a radioactive sample to decay. Okay, pretty simple, not all that elaborate, just the time it takes for half of a sample to decay. For instance, in a 100-gram sample of bismuth-210, in one half-life, which happens to be 5 days, how much would you expect to be left over? 50, okay? So in one half-life, 50 grams of the 100 grams get decayed. That's what half-life means. Okay? So in two half-lives, how much would you expect to be left over? 25, okay? Again, easiest math you'll ever do in a science class is in nuclear, 25. In 20 days, be careful here, how many half-lives do you have in 20 days? 4. So if you had 0 half-lives gave you 100 grams, 1 half-life gave you 25 grams, 2 half-lives gave you 12 and a half. How many do 4 half? Sorry, yeah?
Doesn't 1 half-life give you 50 instead of 20?
That's, did I? Oh,
You said 25. Yeah,
like I said,
25.
1 half-life gives you 50 grams, 2 half-lives gives you 25 grams, and 3 half-lives gives you 12.5, and then after 20 days, 4 half-lives, you have
6.25.
about 6.25 grams. Okay, does that make sense?
Yeah.
Again, easiest math you'll ever do. There is some crazy exponential stuff you can do later on when you get into more advanced chemistry, but at this level of chemistry, all we really care about is how many half-lives do you have, how much is left over. That simple. Okay. And if you use percentages, it's kind of easy. At 0 half-lives, you're going to have 100%. At 1 half-life, you're going to have 50%, which is 5 days. At 10 days, which is 2 half-lives, you'll have 25%. At 3 half-lives, which is 15 days, you'll have 12.5%. And at 20 half-lives, you'll have 6.25%. Sorry, 4 half-lives, 20 days. 25 days is 5 half-lives, about 3%. Pretty simple stuff. We're going to do a practical lab where we find the half-lives of Skittles on Thursday. So don't be gone on Thursday. You can eat them. Yep. Yeah, Skittles are great. Nobody's allergic to sugar, so we'll have Skittles. Oh, that reminds me. Shoot. Alex and I need to prepare the lab today. Oh well, we'll do it today. Okay, half-life practice. So pretty simple stuff. Again, the math is not that exotic. What you need to ask yourself every time you do a half-life exercise is how many half-lives have gone by? So how many times has the sample split in half? Okay. We're going to spend tomorrow working on a half-life worksheet. 9 exercises. And then we'll start our lab. Okay, the half-life of cobalt-60 is 5 years. If you have 10 grams of cobalt-60, how much do you have after 15 years? Don't blurt it out, write it down. All right. How many half-lives have gone by in 15 years? 3. So if you started at 10 grams, how much did you have after the first half-life? 5. After the second half-life? 2.5. And after the third half-life? About 1.1, 1.12 grams. Does this idea make sense? Okay. Question?
Shouldn't it, since, alright, so it goes, the first one goes to 5, the second one goes to 2.5, right? Shouldn't it be 1.25 instead of 1.1?
No, it's 1.125.
It's 1.125. But 1.1 is close enough.
I know, but 2.5 after that is 1.25.
Okay. No, it's not. 2.5 divided by 2 is 1.125. Oh, it's not? 1.25. Okay. 1.2. Moving on. Americium, which I don't know why it's called americium, not maricunium. Maricunium, 242. Has a half-life of 6 hours. If you started with 24 grams and you now have only 3 grams, how much time has passed? Again, don't blurt it out. And don't just divide, because that doesn't work. All right. So, if you started with 24 grams and you now have only 3 grams, how many half-lives have gone by? 3 half-lives? So, we started at 24, that's 0 half-lives. At 1 half-life, we had 12. At 2 half-lives, we had 6. At 3 half-lives, we had 3. So 3 half-lives went by. How much time was that? 18 time units. Good, 18 hours. Next. Oh, question.
So like, I get that after a half-life, it loses half its mass, but like, how does it get rid of that mass?
It decays in whatever mechanism it uses. It might decay through alpha, beta, neutron, some other exotic type. It decays somehow. Yeah.
Does it decay into just like carbon dioxide?
No, it decays into whatever. Guys, the question was, it decay into carbon dioxide. It decays into whatever it decays, whatever it happens to be. So, like bismuth decays into thallium. So bismuth decays into an alpha particle in thallium. So it decays into whatever mechanism it uses. And it would be impossible to memorize it all because there are hundreds of elements. Each one undergoes hundreds of decays. Yeah?
So half-lives are just big decays.
Yeah. We needed a benchmark, we needed a ruler, and the ruler was how long it takes for half of it to go away. It's easier than third lives, I guess. Okay. So, iodine-131 has a half-life of 8 days. If you have 8 grams of iodine-131 and 16 days pass, how much you got left?
Put 1 cup, get it 50, and then every time you get to keep adding until you get to that weight again.
Hey, we're all learning. Okay, if you need more time with this, give me a thumbs down. We're good? Okay, so 8 days, 16 days pass. How much half-lives have gone by? 2. 2? What's left?
4.
Well, we start with 8 grams. And then first half-life we have? 4. Second half-life we have? 2. All right. Next, tin 126 has a half-life of 100,000 years. How many years does it take to reduce 100 grams to 12.5 grams? And again, don't blurt it out. Work it out, don't blurt it out. It doesn't matter. We'll get to that after we answer this one. Question?
So what it's saying is that like it would take about 100,000 years for it to go to 50 grams?
Mm-hmm.
Okay.
I see some of you using your fingers. If any of you complain about the math in chemistry and you're using your fingers, math is too hard in chemistry. They're using their fingers. It can't be that hard if they're using their fingers. Okay, who thinks it's going to take 100,000 years? No one? Okay. Who thinks it's going to take 200,000 years? No one? Who thinks it's going to take 300,000 years? Oh yeah, 3 half-lives. Oh. So, okay, now those so far have all been whole half-lives. The only crazy math we run into is when you have fractions of half-lives. And I'm basically going to tell you right now that in this class, you can just estimate and you're going to be okay. So with your neighbor, try to figure out how many half-lives have gone by to take a 100-gram sample and turn it into a 5-gram sample. And again, if you estimate, that's okay. Yes? Doesn't matter. Well, to give you an example, to get you started, guys, after 0 half-lives, you got 50 grams. After 1 half-life, how many do you have? 25 grams. So finish the chart and estimate how many half-lives have gone by, or fractions of half-lives have gone by when you're down to 5 grams. Daryl.
Wait, so is it like Price is Right rules, closest without going over?
No, just estimate it.
Wait, what if 1 half-life is 50 grams and then 2 half-lives? Yeah, 25 grams.
Yes. Alex, if you need something to pour, there's beakers over here. So, who got a number larger than 4? Okay, so what did you come up with? Just throw a number out. 4.75? 4 1/4? Okay. So obviously we're closer to 6.25, so I think I'd estimate it about 4.2. 4.2? Okay. And again, the math can get a little exotic when we rub partial half-lives. All you got to do is estimate because your test is multiple choice. Okay. It's not going to be like 4.2, 4.3, 4.4. It's going to be like 3, 3.5, 4, 4.5. You can estimate. You're in good shape. Okay. Give me a thumbs up if you're ready to move on. Okay, moving on. E equals mc squared. Now, without blurting this out, with raising your hand, E equals mc squared. You've all heard about it, right? You think of Einstein. What does it mean? Yeah, you just read me the equation, but what does it mean? Daryl?
Isn't it for nuclear fusion or fission?
It's all those things, yeah. Nuclear fission and fusion. But what does it mean? Well, now you're going to know, and you can tell your parents this afternoon. It means that energy and mass are interchangeable. They are different expressions of the same thing. Energy can become mass, mass can become energy. When we drop a bomb in the deserts of Nevada or Utah, a small amount of energy, a small amount of mass is lost and a large amount of energy is released. Because the math is extraordinary. The speed of light is 3 times 10 to the 8th meters per second. 300 million meters per second. It's big. It's really big. So, practically speaking, what this means is if you want your starship to go to warp, then you're going to have to lose a little bit of energy, or a little bit of mass from your dilithium chamber to produce a lot of energy. Or, if you want to flatten a city, a little bit of mass is going to be lost from your fissionable material in your nuclear bomb to release a lot of energy. Gesundheit. Does anyone know where most of the power from Hoover Dam goes?
California.
Yeah, California. Realize when Hoover Dam was built 80 years ago, Nevada didn't have much of a population. California did, and it needed power. Nevada didn't have much of a population. Even now, when the population of the Las Vegas Valley is 2.5 million, we still don't use all that much power compared to California. So we use a little small amount. But Hoover Dam does produce a lot of power. All that water that's being pulled through those turbines, spinning the generators, produces a lot of electricity. My question to you is, if we were to take the mass of one apple, one small apple like this size, if we were to take all that mass, just 1 kilogram, and turn it all into energy, how much energy would it make? Would it make the energy that 1 Hoover Dam puts out in a year? Half a Hoover Dam? 2 Hoover Dams? 10 Hoover Dams? Not even close, like a fraction of a Hoover Dam? So let's calculate that. The Hoover Dam puts out about 1.5 times 10 to the 16th joules per year. So we set up our equation, E equals mc squared. By the way, the unit for energy is the joule. This is probably the first time you've heard about a joule. It will not be the last time. You've heard about joules before?
Yeah.
Good, okay. Yay! Way to go, elementary school. So yeah, a joule is a special unit named after James Prescott Joule, who showed that different types of energy are interchangeable. It's pretty cool. Anyway, so we're going to use 1 kilogram, that's easy. And the speed of light is 3.0 times 10 to the 8th squared. When you square the base number, when you square the 3.0, what does this become? 9, yeah, 9. So this becomes 9.0. And when you square an exponent, what do you do?
You add.
You multiply it, okay? So 10 to the 8th squared is 10 to the 8th times 10 to the 8th, which is 10 to the 16th. So if we could somehow take all the energy in our apple and turn it all into energy, or take all the mass in our apple, turn it all into energy, we would make the same amount of energy that Hoover Dam produces in 6 years. Or 6 Hoover Dams. That's a lot. Talk about dropping a bomb on somebody. I'm going to drop an apple bomb on you. It's a lot of energy. Which is why you just need a small amount of energy, a small amount of mass in your dilithium chamber to cause your starship to go to warp. Yeah. Don't mess with us, North Korea. I'll drop an apple on you. Okay. This is also what we use in super colliders. What we do is we take particles. Some of you asked about this. How do we make those artificial elements? This is basically how we make artificial things. We take a particle and we speed it up. We speed it up and give it lots of energy. Zoom, 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 zoom. Then we take another particle and speed up and go zoom, 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 zoom. And then we slam them into each other. So we have one particle going zoom, 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 zoom. Another particle going zoom, 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 zoom. Then we open the door and the particles go BAM! Yeah. All that energy they've been carrying turns into mass. And the faster we can go, the more energy we can put into them, the more mass we can get out. So we can make more massive particles. The hope is at some point in the future, we'll be able to make a giant massive particle that's actually stable. Yeah, hasn't come up so far. Yeah?
What happens if two spaceships are traveling at light speed and they hit each other?
Well,
Everyone is dead.
yeah, they would produce a lot of mass. Well, the problem is you can't really travel at light speed, except in sci-fi. But because anything that travels towards the speed of light becomes like energy itself, so you can't really do it. And oh, we totally can. And that when things travel faster than or near the speed of light, they slow down. So you'd go very, very fast and you'd basically stop. So if you had two things traveling at the speed of light, they could never approach each other because time for them are stopped. We'll talk about that in physics. Woo! Yeah. Gravity too. What's really wild is people up in like the mountains, they age slower than people down at the bottom of the mountain. Because time is gravity related. Yeah.
So, like, Star Wars reference, if, like, say they're going at speed of light, if one of them were to jump, would they just, like, smack into the side of the wall? Because, like, they're not technically with the ship.
Yeah. It's not something we can spend a lot of time on. But if you want to talk about science fiction, we can later, but we need to move on. If we get extra time, then ask me at the end of class. Yeah. Okay. So, atomic stability. I promised that we'd eventually talk about what makes something stable or not. What makes something stable or not is the proton to neutron ratio. Okay. Actually write that down. Proton to neutron ratio, that's what determines stability. You actually discovered this last Friday in your simulation. When you added neutrons to the atom, eventually the atom started to shake when it had too many neutrons. Or if you took neutrons away, eventually the atom shook when there wasn't enough neutrons. There's a butter zone where the number of protons and neutrons is just right. The most fundamental thing in all of science, be it chemistry or physics or biology or anatomy, is the idea that at its core, opposites attract while likes repel. Electrons are moving very, very fast around the nucleus. If it wasn't for their attraction for the protons, the electrons would fly off. If you take two electrons and you put them close together, they repel. And you understand this, right? You've all heard this before? Like magnets, yeah. A north pole and a south pole, they attract. A south pole and a south pole repel. Now, if an electron repels another electron, shouldn't it make sense that a proton in the nucleus would also repel another proton in the nucleus?
But are they attracted
They
to
do.
the neutron?
No, they're not. The protons in the nucleus are repelled against each other. They do not want to be in the nucleus with other protons. So there has to be some sort of thing, some sort of force that holds the protons together. What is it? Neutrons. And we just went ahead and said, protons repel each other. So neutrons act like nuclear glue. We went ahead and said, we're not going to give it a name, we're going to call it nuclear glue. Which is great, because the thing that gives the neutrons nuclear glue are, I'm not making this up, gluons. Gluons are the name that we're going to assign to what makes the neutrons create a web of glue that holds the protons together. This is the basis of what's called the strong nuclear force. So the protons are all hanging out in the nucleus and they're like, I want to get apart. I hate you, proton, because I'm a proton too. And likes repel. And you're like me, so we repel. And the neutrons are like, hold on, buddy. I'm going to create a web of glue that holds them together. So, yeah, the web of gluons, again, this is our current level of understanding. The web of gluons that the neutrons create holds the protons together. That's called the strong nuclear force, the strongest force in the galaxy. Has a light side? No, it doesn't. So if the ratio of neutrons to protons gets way off, then the atom becomes unstable. If there are too many neutrons, those neutrons have nothing to do, the atom becomes unstable. If there are not enough neutrons, the protons can't hold each other, or the protons can't be held together, and the atom becomes unstable. This is the part where you use a calculator. Okay, we remind ourselves that the nuclear charge, the bottom number, is a number of what? Protons. So uranium-92, the 92 tells us we have 92 protons. Lead-82 tells us we have 82 protons. Oxygen-6 tells us we have, sorry, oxygen-8 tells us we have 8 protons. Subtract, and we can find out how many neutrons we have. This is where you bang on your calculator. Bang on your calculator. Find out how many neutrons we have in uranium-235, how many neutrons we have in lead-206.
Lead, there's 124.
124? Uranium? 143?
Yes.
Okay, so now divide these. What is the ratio of neutrons to protons in each of these cases? What is the ratio of neutrons to protons in each of these three cases? So divide the big number with, what do you got?
1.5.
For,
Very estimated to 1.5.
for uranium?
Yeah, uranium.
Okay. 1.5, this is the NP ratio. And for lead? Anyone have lead? What do you got, Geneva? 1.66. And for oxygen? 1. 1 to 1. Oh. 1.6?
No, just 0.66.
Oh, big number over small number. It's the neutrons to the protons. The ratio of the neutrons to the proton. 1.5? Okay. Okay, so those are the butter numbers. For large nuclei, the protons start to overwhelm the glue, so you need more. Here we go. For large nuclei, the protons start to overcome their glue, so you need more neutrons. For a small nucleus, a 1-to-1 ratio is good. For a large nucleus, a 1.5-to-1 ratio is good. So for larger nuclei, like uranium and lead, you need 1.5 as many neutrons as you have protons. For a small nucleus, nitrogen, sodium, magnesium, 1-to-1 is a good ratio. So these are the important numbers that you need to remember. It's a neutron to proton ratio, and for a large nucleus, you need 1.5 neutrons to protons. For a weak nucleus, or a small nucleus, 1-to-1 will be just fine. I'm sorry? Hand on hand? Pedo a pedo, foot on foot. Taco a taco. One taco on one taco. Right, okay. So are we ready to move on? We got a few minutes left. More? We have more Skittles. Thursday. Lab's on Thursday. He'd be back there shaking with all the sugar in his body. Okay, we just have 2 little things left to talk about and 5 minutes with it to do so. So we are going to move on. You can review this later. Okay, band of stability. You don't need to write anything down here, but this is basically an illustration. It's in every textbook. It's online all over the place. This is the band of stability. So as our atoms get bigger, we approach the 1.5 range. Smaller atoms, the 1 range. And then in the middle, 1.2, 1.3 range is just fine. Okay, we're going to talk about mass defect next week. We're going to skip this over until next week. Finding energy. Okay, nuclear fission. Nuclear fission, we talked about this briefly last time, is the process of taking big things, breaking them apart. And when we have those big things, we break them apart, they release energy, according to our E equals mc squared. Now, how it's usually done is you get a half sphere of fissionable material and another half sphere of fissionable material, and there's something in between that keeps them from getting together. Then you cover those half spheres with explosives, and you detonate like conventional explosives like C4. And you detonate them, and those conventional explosives squish that material together. And when it squishes together, it gets what's called a critical mass or a critical density. Now, the neutrons are so close together that they cause each other to fizz. Squish, boom. That's what you get. You get a mushroom cloud. It's a little fire hat. Isn't it fusion more powerful though? It is, yep. And we're not going to get time to talk about it, about nuclear fusion, but nuclear fusion is more powerful. It does release more energy, and it would be a really great power source for us. The problem is we haven't figured out how to make it work. So we can make fusion go, but the amount of energy it takes to make it go is usually more than we get out. So the moment we are making more energy than it takes to make fusion go, that's where our energy revolution goes. And happy days, no more fossil fuels, everybody's happy. So it's your job, your generation's job to make fusion work. And if you can't do it, it's going to be your kids' generation's job to make fusion work. Then it'll be their job. Yeah. Yeah. Energy research is kind of not all that done all that much now, but